All right. So my safety moment today is working alone in the lab, which might be a little bit more common due to COVID-19 and our research lab situations. So working in the lab alone is always a challenging part because working alone in the lab plus hazardous chemicals can lead to special and greater potential hazards and risk. So the risk of injury is usually increased, and so is the risk of the seriousness of the injury because the injured person might not be able to contact for help in the event of an incident. So there are ways to mitigate the danger because there are many researchers in our lab or in our department working alone. So if you must work alone, it's always best to use the buddy system. So don't work without someone else knowing where you are and what you're working on. And during COVID, that can even be a virtual buddy, but just making sure you're being smart about everything. So you should also make arrangements to check on each other periodically to make sure everyone is still okay and responding, as well as you need to be smart about what you're working with and what experiments you're working on. So this means limit activity to certain hours where there might be people nearby, limit activity to certain materials that you know are safe, and establish a system to contact help immediately, as well as being familiar with the chemistries, your chemicals, and equipment. And this usually entails really no working with new experiments if you're totally working alone. Um, so with that, I'd like to introduce our speaker today. So our speaker today is Amy Morris from Fort Lewis College. Amy received her PhD in chemistry from Colorado State University in 2009 under Professor Richard Fink. She worked on various protein aggregation kinetic models as well as inorganic studies of ruthenium catalysts. She then went on to become a postdoctoral fellow at Brandeis University in Massachusetts, and then became a faculty member at the Massachusetts College of Pharmacy and Health Sciences in Boston. In 2012, she became a faculty member at her current institution at Fort Lewis College. So her work at Fort Lewis College, which is a primarily undergraduate institution in Durango, Colorado, includes many teaching achievements as well as fantastic research with undergraduates. She has received many awards recognizing her achievements, including the Fort Lewis College Skyhawk Appreciation Award, as well as an NIH Build Program grant focusing on biomedical learning and student training. So Amy, we're so happy to have you and listen to all of your exciting research, as well as have you talking to us throughout the day with all of our events. So thank you again for agreeing to be our guest at our inaugural Curie Club Colloquium, and I'll go ahead and pass it over to you.
Well, thanks, Erin, for the very nice introduction. Let me just make sure this is all up and running here. And so I wasn't sure if everyone would know about Fort Lewis College, so I thought I would start with just a super brief background. So we're a primarily undergraduate institution, as Erin mentioned. We have about 3,300 students currently, and over half of our students are students of color. We're a non-tribal Native American serving institution, and we have 40% of our student population identifying as Native American or Alaskan Native. And so a primary goal at our institution is really to educate and bring research opportunities to our student population and hope to increase the diversity in our PhD population, especially within STEM. And so I've been at Fort Lewis since 2012. We're in a very rural, geographically isolated area in Durango, Colorado, which is beautiful, if any of you have been here. And we're very close, actually, geographically to the Navajo Nation. So we do have a lot of connections, and we're creating more connections into that region. It's also really exciting for me to see not only Erin, but I also saw Shecky on there, so a couple of alumni from Fort Lewis. We're always happy to follow our graduates and see some of the amazing things that they go on to do. Fort Lewis College is a small public liberal arts college, but we're also nationally recognized by the NSF as one of the top 20% of undergraduate institutions that send their students on to PhDs in chemistry. So we're very proud of the work that we do at Fort Lewis. I had to really retrain myself when I took on this role. I was used to that high productivity, um, research minded mindset that we get into in graduate school and in postdocs. And so I was used to that, results, 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 publish, publish, publish. And I'm sure some of you can sort of, wrap your mind around that mentality right now. And I had to kind of rethink my research agenda at a primarily undergraduate institution. My primary goal here is to train undergraduate students. So it would be much easier for me to go into the lab myself and to run these experiments. But really, our goal is to give students the skill set, the confidence, and the ability to go on and do these great careers, whether that be in graduate school for chemistry, biochemistry, whether that be medical school. I have students that have gone on to PharmD programs. And so coming up with unique and interesting research projects that I can do with undergraduate students. And then the other key here is that undergraduate students, especially in STEM, are extremely busy. And the time they have to work on research becomes very limited, especially within the academic year. And so not only do I need to come up with projects that are doable on an undergraduate level and easily understandable and explainable in terms of big picture ideas, but I also need these projects to have small pieces that students can work on and pass along to other students. And we take these small pieces over time. And hopefully what I'll tell you about today is a bit of a story, which is multiple students worth and years of work of putting these little pieces together. We find it really hard at PUIs to make progress during the academic year. Most students can commit about 3 hours a week to research. When you extrapolate that to the amount of hours you're all spending in your PhD programs per week, it's a lot harder to make progress in a short period of time. So one of the projects that I've been working on with undergraduate students has to do with this idea of developing prodrugs based on cobalt metal centers. And so our background and inspiration for this whole project really involved the amazing accomplishments and the huge amount of work that's been done over the past 30 years on these two ruthenium-based compounds, NAMI-A and KP1019. So these are the first two ruthenium-based drugs to enter into clinical trials. They have undergone a lot of research, and there's been some really interesting discoveries based on these two compounds. So NAMI-A is able to decrease the speed at which metastases grow, but there's not a lot of evidence that it does much for primary tumors. And so it's an interesting chemotherapeutic. And then we also have KP1019, which goes after primary tumors, but not after metastases. And the really big picture idea here is that these are really the first metal-based chemotherapeutics that showed a vast difference in cytotoxicity. And so our traditional chemotherapeutics are platinum-based, they're highly cytotoxic. We know that patients see a lot of side effects because they aren't discriminate. They don't go after only diseased tissues, they go after diseased and healthy tissues at the same time. And so seeing this big difference in cytotoxicity with using these ruthenium-based drugs was a really big development in the area of bioinorganic chemistry and in the whole idea of using metal-based compounds for medicinal properties. And so taking some inspiration from these two different, very historic and very exciting new complexes, we wanted to look into utilizing a different metal center, but also taking some of the knowledge that was learned about these compounds. And so you'll see they have pseudo-octahedral geometries. Ruthenium has common oxidation states in the +2 and +3 states. And so my first idea was to look in the first row transition metal series. Well, right above ruthenium is iron. Clearly that's not going to work very well because we have a lot of iron chemistry going on within our bodies. But I had an idea about cobalt, and I thought cobalt has mainly pseudooctahedral geometries. It has oxidation states primarily in the +2 and +3 state, and there are a lot of similarities. One of the reasons these ruthenium compounds were so highly investigated is that they are low spin D5 complexes. They're categorized under the kinetically inert, right, category, although looking at these in solution, they definitely undergo substitution reactions. So we can classify them as kinetically inert, but we've also learned a lot about these two different compounds and the degree of hydrolysis they undergo, and ligand exchange reactions. And in fact, NAMI-A is now thought to basically lose all of its original ligands and become a naked ruthenium that can then go on to bind to different Lewis bases within the body. Whereas KP1019 has very drastically different properties. It still undergoes ligand substitution, but there's a lot of evidence building that it remains with at least one of those indazole ligands attached. And so looking at these structures and thinking about the interest in this area, we decided to investigate cobalt, and we decided to start looking at, lost my mouse here, and it's still gone, so that's okay. But in green, I have the imidazole ligand highlighted on NAMI-A, and in KP1019, I have the indazole ligands highlighted in blue. And so what we wanted to do was to take the inspiration of the ruthenium compounds and think of how we could use these imidazole and indazole ligands and complex them onto cobalt metal centers, and what kind of complexes could we make and what kind of properties might these have. And so this was sort of our original inspiration and idea. Now, there was one gigantic challenge as soon as I entered the lab, and that gigantic challenge was, one of the things I didn't mention is that both of those ruthenium compounds only utilize monodentate ligands. They utilize things like chloroligands, and also they utilize N-heterocyclic neutral ligands. And so if you go into any of our normal chemical suppliers, you'll find some cobalt-3 starting materials that you can buy, but they all have chelating ligands attached. So there are no cobalt-3 commercially available starting materials that have a high degree of ligand substitution that is immediately possible. So you can buy things like cobalt-3 plus with ethylene diamine ligands attached. But we know that ethylene diamine ligands are fantastic chelating agents, and it's very hard to kick out an ethylene diamine ligand, especially if our overall goal is to then reattach only monodentate ligands back onto that cobalt metal center. And so this was our first challenge within the lab. And so I had my students investigating. We started off on kind of a crazy idea. I said, let's try making we'll start with cobalt-2 starting materials, because you can buy something like cobalt-2 chloride either in its anhydrous or hydrated form, and see if we can both oxidize it up at the same time as we add ligands. And we tried many different strategies utilizing heterogeneous catalysis and different ideas for that both oxidation and addition of ligands at the same time. And that process wasn't going so well in the lab. And so we switched gears pretty quickly. And one of my favorite things to do is to go into the old obscure literature. And so when I went back into the literature, I found a paper that was written in German from 1906. And the paper was for how to make trans dichlorotetrakis pyridine cobalt-3 chloride. And so I went into a Google translator, and there was also some more recent work on this same compound. Nothing to do with potential prodrug properties, but there has been some work on making this compound in particular. And again, that was relatively old literature as well, from the late 70s, early 80s. And so what we found is that they actually made this cobalt-3 starting material by starting with cobalt-2 chloride and using chlorine gas as an oxidizing agent in the presence of pyridine ligand. And you can then both oxidize up your cobalt, add your pyridine ligands, and you'll get your chlorine counterions possible from this process. So it's a really cool redox coupling reaction. And I love these kind of reactions because as I'm teaching my classes in inorganic chemistry and even general chemistry, we cover these very basic topics. And so being able to take what the students are learning in class and showing them why this redox works by looking at the redox couple and having them calculate this out, I get excited about these kind of connections. So we reproduced some really old literature and we made this cobalt-3 starting material. And this was really the start of this project. So we finally had a cobalt-3 starting material and we could start to do some ligand substitution and start thinking about how we wanted to build new molecules now that we had a starting material. And so you'll notice throughout my talk, I said my primary goal is really to train undergraduate students. And so all of this work has been done by undergraduate students, and I'm going to highlight a few of those students kind of as I go. So the first student that worked on this project and got our starting material, her name is Kayla Hart, and she did a fantastic job in my lab, and she worked over one summer to accomplish making this starting material, and we scaled it up in vast quantities, and we still have some in the lab that we're using today. And so Kayla is now a commercial real estate agent in Bozeman. I kept trying to get her to go to graduate school, but sometimes it's just not a good fit, right? And that's okay too. But Kayla did an amazing job. I had a lot of issues actually on my campus with our environmental health and safety officers. They did not like me having chlorine gas within the lab. We're an undergraduate institution. They're not used to seeing some of these more hazardous things, but I did make a beautiful setup, and we used a water trap to catch the excess HCl that is always a contaminant within the chlorine gas canisters, and we made this beautiful reaction all within the fume hood, very safe, no students, right, had any issues with this. So once we had that starting material, then we went about trying to complex new ligands. So the first ligand I'm going to talk about is the indazole ligand. So again, that inspiration came from the KP1019 structure. And so we started thinking about how can we do these ligand substitution reactions now that we have this cobalt-3 starting material. And so the strategy that we used is that we knew we needed to kick off those red pyridine ligands. And we knew that chloroligands are relatively easy to substitute in and out, but the pyridines were going to be our biggest problem. So we needed to kick out the pyridine ligands. So what we decided to do was set up a reflux reaction, which is pretty common in a lot of these prodrug syntheses. And the reflux conditions that we were looking at is we wanted to be above the boiling point of pyridine, but below the boiling point of the indazole. And so I had my students go in and just do a whole series of solubility tests, taking the cobalt starting material as well as the ligand that we wanted to introduce. So just find me what kind of polarity range do we have to work within, and then we went back and matched for melting points. Turns out we landed on one of my least favorite solvents to use, which is dimethyl sulfoxide. So DMSO is great because it solubilizes almost anything. The problem is that it has an incredibly high boiling point. And so once you introduce something into DMSO, it's incredibly hard to get all that DMSO back off, right? But we decided to start here. It solubilized everything. It hit our criteria for trying to introduce these new ligands onto the cobalt metal center. And so we set up a reflux reaction, and then we optimized conditions for that reflux reaction. The smallest time scale I could get this down to get it to actually complex was 24 hours. So we had a 24-hour reflux, and we also found that our best conditions involved using a high amount of excess of the indazole ligand. So our best conditions were a 10-to-1 ratio of indazole to that cobalt starting material. And I have this structure drawn here, but we also found that we had some hiccups along the way. But I also want to give a massive amount of credit. So the student you see pictured here is actually presenting a poster on this work at the National ACS meeting. And that student's name is Natalie Joe. Natalie is currently a fourth-year PhD student at Johns Hopkins, working on her PhD in cellular and molecular medicine. I had the pleasure of having Natalie in my lab for almost 3 years as part of an NIH-funded program called Maximizing Access to Research Careers. And that program really supported Natalie's work in my lab. That program allows these students to earn a monthly income for doing research with a professor without having to have outside jobs like many of our students do. And so without that program and that time commitment from Natalie, we wouldn't have been able to make such amazing progress on this particular compound. So Let me tell you the good news about this compound. So the good news is that we took one of those super exciting ligands that we had inspiration from, and we attached it to a cobalt metal center. And I didn't get into this at the very beginning, but part of my idea for designing this project was that I knew cobalt 3 is D6, and in a perfect octahedral geometry, and with the right ligand combinations, it will be a low spin D6 complex, meaning it's diamagnetic, which means that we can easily use the probe of proton NMR to see if we have in fact complexed things like indazole ligands onto cobalt metal centers. So again, also I have to think about the instrumentation that we have available within our own department and how we might be able to probe and look for these different things. And so what you'll see is, I love this NMR. It was one of the first NMRs I got super excited about. And then I also get cautious at the same time whenever students show me new results. But this is the beautiful NMR that shows the amazing splitting pattern that matches that of indazole. And you'll see the assignments that we came up with. So this was the good news. I also immediately always ask students, as soon as they show me an NMR this exciting, go back into the lab and add some free indazole ligand into that NMR tube and go run it again, right? I need to make sure that it's actually complexed. And so we did that experiment as well. You'll see a whole new set of peaks that show up for free indazole. So it has in fact complex to the cobalt metal center. We ran some magnetic susceptibility on the solid state sample to show that it was diamagnetic. And so we had some really promising results, but we were also seeing some things that we couldn't quite answer. So one of the things we were seeing is that not only were we seeing, we ran this in deuterated DMSO, again for solubility reasons, but we were seeing a splitting in the DMSO peak. So not only residual solvent, but we were also seeing a peak that indicated DMSO was binding to our cobalt metal center. And so if we're thinking about prodrug properties, this is actually good news. It means that it has lability within the ligand system, but also DMSO is sort of that double-edged sword in that it's solubilizing things, but now it's a non-innocent ligand that can also undergo substitution reactions. So we had some things going on here. We ran some carbon NMR to also show the same thing. We did in fact have this beautiful complexation. Clearly we have a high degree of symmetry within the compound because we only saw one set of peaks for a bound indazole to the cobalt metal center. And so the solution state was really exciting. And we had very consistent results that we were getting a high degree of symmetry. We were in fact binding indazole onto the cobalt metal center. And then we tried to do some solid state characterization, and this is where things got really hard. So we sent this off for elemental analysis. And again, it was in DMSO. So we dried it under high vac for very long periods of time, trying to remove as much DMSO as absolutely possible. And when we sent it off for elemental analysis, the results came back very bizarre. And so we tried every combination of things that were in that reaction to come up with explaining the elemental analysis data. And no matter what I did, nothing matched. So it was way too high in carbon content. And so I still, to this day, can't tell you exactly what was going on with elemental analysis. And we sent it off multiple times. So it wasn't a one-off. And also the other thing I should mention is that one of the things I worry about is reproducibility. So we reproduced this experiment at least a dozen times with consistent NMR results. So it wasn't a reproducibility problem, but our solid state wasn't matching our solution state, our beautiful, pure, right, NMR. And so we tried some other characterization methods. I have a collaboration up at CSU where I did my PhD, and we were able to grow these beautiful green needle-like crystals of this compound. We grew them in DMSO. They were incredibly temperature sensitive. So I could grow them in the freezer. If you take them out of the freezer and they start to warm up, they immediately resolubilize. So we had some issues with transport, but I finally figured out a way under dry ice to ship them up. And then when we put them on to diffract, the entire thing fell apart. And the only thing we saw in the diffraction pattern was free indazole. And so we had a lot of issues in the solid state this thing just wasn't stabilized in the solid state. Something about the packing just wasn't working. And so I'd love to tell you that this has a happy ending, but this is still a mystery in my lab. However, what I do want to tell you is that we learned an immense amount of information from this very first system. And what we learned is that we could really utilize that cobalt-3 starting material and really play with those reflux conditions to be able to complex different ligands onto cobalt-3 metal centers. And so while we're still working on figuring out what's going on with indazole, oh, and by the way, I also happened to have a student at the time that was going up to CSU on a visit because she was thinking about going to graduate school there. And so I actually made her transport crystals up for me so I knew they wouldn't get all shaken around within the mailing system. And those still gave us a diffraction pattern for only the indazole ligand. So I'm not sure exactly what's going on with that particular one, but we're not getting highly stable systems within the solid state. And we also tried to run electrospray ionization mass spec in the high res, and that also was giving super bizarre results. So anytime you introduce energy into, let me go back for a second, anytime you introduce energy into the system with cobalt bound to indazole, it is making the entire structure fall apart. So I'm still trying to figure out that particular mystery. That one continues to haunt me. But we did then learn a lot about these conditions. So what we did next is we went to imidazole. And we decided to use our same strategy. Only this time, finally, we got away from my nemesis, DMSO, and we found that our solvent matched this time for a higher boiling point than pyridine, but lower than imidazole. We found methyl isobutyl ketone, which is not a super common solvent to be thinking about, but that's the one we found that seemed to be working. And the two students that worked on this project, I actually got to keep them for 2 summers. And so what you'll see is that's when we make the most progress on our research because we have dedicated time in the lab. And when I had these students for 2 summers in a row, they were both highly productive, motivated students. We made a lot of progress in this arena. And so the 2 students that worked on this project are Hannah Nash and Becca Miller, and they also went and presented some of their research at an ACS meeting. Hannah is now a 2nd-year student in the PharmD program at CU Denver, and Becca is a PhD candidate in materials chemistry at Boise State. And so this gives me such joy to talk about these students because not only are we doing the research, but these students gain the skills they need to be successful in the next step, which is really what my job is all about. So we found these new conditions. You'll notice we got the reflux time down quite a bit. This goes down to 2 hours. We did a lot of work in tweaking conditions. We found the best conditions in this particular case was to use just a slight excess of imidazole. So we used 5 equivalents of imidazole for every 1 equivalent of the cobalt source. And we see, again, a very similar reaction as the one I showed you for indazole. Only this time things went a little bit more smoothly. And so we had very nice NMR data, very consistent, very clean for one product, high degree of symmetry again. Again, we ran those control experiments with having free imidazole in there to make sure that the imidazole was in fact bound to the cobalt metal center. And we tried for a super long time to crystallize this product. I really wanted to get single crystal X-ray diffraction data. It turns out that this does not want to crystallize. And I'll tell you why that's maybe a positive thing here in a little bit. So we couldn't get crystals, but I wanted to have definitive structural data on this compound. And so what we did, and you'll see that I've assigned this NMR, but we couldn't just assign this NMR based on the proton and carbon that we had run, because you've got interesting things going on here in terms of possible meta effects and which is the most upfield versus downfield proton, right? So what we ended up doing was, and this was really fun for me because when I teach undergraduate classes, sometimes the light bulb goes off. I was teaching synthesis and spectroscopy, and I was like, oh, let's do some 2D NMR. This sounds great. We'll be able to figure out which proton is which. And so the first 2D NMR we ran was the proton-proton correlation. So we ran a COSY, and the only thing this really told us is that the proton that shows up in the middle is correlated to both of the other two protons. Well, that's not very helpful, actually, if you're looking at protons A, B, and C. And so we went to some other ideas. We tried some nosy experiments. We tried some other things. And finally, one of my organic colleagues said, "Have you run a difference NOE yet?" And I was like, well, that's a great idea. So we went into the lab. I say we, I believe I went into the lab on this particular case, and we ran a difference NOE on this particular compound. And so when we irradiated the most downfield proton in the aromatic region, we saw a super strong correlation to that NH peak. And so that ends up being your proton A signal, right? And then when we irradiated that central aromatic proton that we were seeing, then you see a correlation to what ends up being proton B. And so we saw these different correlations, and when you irradiate what ends up being proton C, which is the furthest downfield of the aromatic protons, you see that NH is really interacting there. And so we were able to then go back by looking at irradiating these different peaks and finding the neighbors, which protons were correlating to which protons. And then from there, we could go on and do the heteronuclear correlation to be able to figure out which protons were then attached to which carbon signals. And that's how we ended up with our final assigned NMR spectra for this particular compound. And again, that high degree of symmetry within the equatorial plane for those imidazole ligands attached in the transchloros are what makes this have all of those chemically equivalent, beautiful proton signals. So wanting to make sure that I was being a good inorganic chemist, as many of you know, what you do is you throw every possible physical method that you can at these things, right? And so one of my colleagues is an analytical chemist, and so Dr. Kelly Cole was doing mass spec as some of her research, and so we didn't have high resolution mass spec available to us, but we did have some lower resolution mass spec. And so I had a research student that was actually doing research in my lab as well as Dr. Cole's lab at the same time. And so he said, I'll go run your mass spec. And so he was able to take our compound. And when we look at the electrospray mass spec, we can not only see the parent cationic coordination complex, but we could also increase the normalized collision energy. And as you increase the normalized collision energy, we also saw more of the fragments populating. And so this was really strong evidence for us, again, based on the structure of what was happening there. And so I was working on submitting this to a journal, and one of the reviewers really wanted to see IR data. And I was like, okay, we can do that. And so the IR data, again, just shows the difference between the stretching frequencies that you'll see for free imidazole, and when it's bound, what you really lose is you lose the disappearance of the hydrogen bonding vibrations that exist around 2800 to 2400 centimeters to the -1 in free imidazole, and you see this shift happening. And so this has been observed in some other cobalt imidazole complexes as well, and so just further evidence that it is in fact bound. So we also started doing some solution state analysis in terms of UV vis. And again, this is something I teach in my inorganic classes, so it was fun to tie this in for the students. And so we took the compound that we had made and we dissolved it in water. And we saw these beautiful D to D transitions that correlate actually with that D4H point group. And it actually correlates with the tetragonal distortion in these low spin complexes. And so we were seeing these D to D transitions that are common in these types of complexes. So I mentioned earlier that we had tried to actually grow single crystals of this compound, and we were unsuccessful. One of the reasons we were unsuccessful has to do with the solubility of this particular complex that we had made. And so it turns out that in terms of a prodrug, this is fantastic news, but this is only soluble in very polar solvents. So it's really soluble in water. That's good. DMSO and methanol. Beyond that, we weren't able to really stretch it into the organic solvents to try to crystallize this out. The other thing we were seeing, so as we took this UV vis of the compound, we noticed that there was a visual color change happening within our actual cuvette. And so I'll just show you kind of a before and after of that. But so we took the UV vis of this and then we just left it there and we took another UV vis 36 hours later. And what you'll see is a blue shifting of those two maxima. And so the blue shift is likely due to ligand exchange. The only things that were in that cuvette were water and our compound that we had assigned as that trans chloro with the 4-imidazole ligands. So the most likely thing to be happening is that the ligand exchange is involving removal of a weak field ligand like a chloro ligand and replacing that with a stronger field ligand like either imidazole or aqua. And so we saw this visual color change happening. And we also wanted to investigate what was going on in terms of oxidation state of this compound. So when I mentioned at the very beginning that our inspiration came from those ruthenium compounds, those ruthenium compounds and their mechanism of action is very, very highly debated in the literature. One of the potential mechanisms of action is that the ruthenium 3 metal center becomes reduced, and it is the reduced form of ruthenium that actually causes a whole cascade of events to act as a chemotherapeutic agent. However, I say that's hotly debated because over 30 years of studying, what's happened is that you have this ruthenium compound that has a high degree of ligand lability, so it loses ligands. So you end up getting a high degree of speciation within a complex system like the human body. Which of those species is actually now doing the mechanism that causes it to have the therapeutic quality? That's a really hard question to answer. And so there have been many studies involving how does that ruthenium compound work? And one of the things that I can definitively say is that it causes a lot less side effects. And there seems to be a mounting degree of evidence that the ruthenium doesn't bind to DNA targets like traditional platinum chemotherapeutics, but it seems like it might be binding to protein targets. Specifically, it looks like amino acids with things like nitrogen and oxygen donors. So there's been some really cool studies in terms of XFs and things like that to probe the oxidation state, as well as things that it can bind to within these complex systems. And so, because it's a hotly debated idea, I still wanted to investigate, can this cobalt complex become reduced under biological conditions? Whether or not that turns out to be the mechanism, if this has potential as a prodrug, it's something that we needed to look at. And so what we did is we took this cobalt-3 complex and we introduced a biological reductant. We introduced ascorbic acid, and we did in fact see evidence by UV vis that this can become reduced to cobalt-2 in the presence of a potential biological reductant. And so again, whether or not this becomes reduced, still hotly debated in terms of ruthenium systems, and cobalt systems may turn out to be completely different, but it's also something that's super interesting. So because we noticed these changes by UV vis, even in the parent cobalt-3 complex, we wanted to investigate the kinetics of the ligand substitution a little bit further. And so I had my students run a whole series of NMR reactions. So we took the parent cobalt-3 complex, we dissolved it in D2O, and we took the NMR. And as quickly as we could dissolve it in D2O and get it into the NMR, which took 4 minutes to get everything set up and actually run the experiment, we already saw the appearance of some peaks that we don't normally see. So this is very, very labile in the presence of water. There's definitely substitution reactions that are happening very quickly on minutes time scale. And so we kept that NMR tube in there and we monitored what was happening to the NMR spectrum over time. And the other thing that's really cool is that we actually see a color change again, visible color change. So the NMR tube starts out green and it goes to a red color by the time we're done with this particular timing of the reaction. And so one of the things you notice is that that high degree of symmetry becomes broken very quickly. And that there's definitely lability and ligand substitution happening in D2O. And we predicted that the species you end up with in the end would involve several ligand bond breaking and remaking steps to end up with a no longer symmetric, right, cobalt 3 complex that now has one chloroligand and one water, or more likely in this case, D2O ligand attached because of how much D2O would be in there. And so this is what we think is happening over time in the presence of water. In terms of a prodrug, this should be really good, right? Because what a prodrug we think is doing is undergoing a series of ligand substitution reactions. It might also be undergoing some sort of reduction mechanism in order for the active species that's actually doing the therapeutic to work. And so going back to taking that NMR data and also looking at adding that biological reductant, we don't know for certain if this will become a high spin complex, but what we do know is if cobalt 3 does in fact become cobalt 2, in the presence of biological reductants, no matter if it becomes high or low spin cobalt 2, it will have unpaired electrons. And so while cobalt 3 is considered low spin D6, kinetically inert, diamagnetic, we know that if this undergoes reduction, you will get an unpaired electron. And that will become more reactive than the cobalt 3 parent compound from which it came from. And so again, whether or not it becomes reduced, again, not definitive at this point, but we think we have some really good evidence that this might function as a potential prodrug, not only due to the ligand lability, but also due to the fact that if it does become reduced, it would have a high degree of reactivity. So, the next thing we looked at was some cyclic voltammetry. So the top dotted line one has the internal standard ferrocene in there to see your ferrocene to ferrocenium couple. And the bottom is just our cobalt compound. And so you'll see as we progress towards more negative applied voltages, we see the cobalt 3 get reduced to cobalt 2. This is actually an irreversible reduction that happens within our cobalt compound, which again is very common in similar cobalt 3 compounds with multidentate ligands. So there's likely a change in structure. Once you reduce cobalt 3 to cobalt 2, there's likely some other ligand substitutions and changes in structure that happen. And in fact, we see evidence for that even in the cobalt 3 state. But the really important thing about this particular experiment was that you need to have a reduction potential between minus 0.1 and minus 0.5 volts versus a normal hydrogen electrode in water at pH 7 in order to get successful redox cycling within biological systems. And so what we wanted to see, again, we don't know if activation by reduction is happening, but would this complex be capable, right, of being within that redox cycle limit? And what we found is that we have that irreversible reduction of cobalt 3 to cobalt 2 that happens at negative 0.51 volts versus NHE. So we're right on that upper limit in terms of whether it would be possible to reduce our complex in vivo. So we have not done any in vivo experiments with this compound, but we have tried to investigate to the best of our abilities what this might be capable of doing. We've only done this in vitro systems so far. So the last sort of thing we wanted to investigate and that we published on this particular compound is we wanted to see what was going on in some cell line systems. And so I actually collaborated with a biology professor at Fort Lewis, Dr. David Blake, and he ran a series of experiments for me on some cell lines. And so this is kind of a funny story. This was happening over the summer, and he ended up calling me to tell me the results. And when he called to tell me the results, he's like, I have bad news. Everything looks the same as the DMSO control. And I said, that's fantastic. And he's like, what? And so here's why that's fantastic. Remember that the whole big picture idea with these complexes is that we want less cytotoxicity. We want less side effects. We want these to be more selective, right? And so the fact that these were not showing any more cytotoxicity versus a DMSO control was in fact good news in my opinion, because it meant that we might be able to do something with these and not have a high degree of cytotoxicity. And so that was actually a positive result in terms of NAMI-A. So maybe that could also be a positive result in terms of a cobalt compound that's inspired by a similar idea. One of the things I haven't yet pointed out, but I really should, is that the cobalt complexes I've been showing you today do have some fairly drastic differences from the ruthenium compounds that we gained inspiration from. One of those drastic differences is both the KP1019 and NAMI-A are actually coordination complexes that are overall anionic. They have a countercation. The cobalt complexes that we ended up synthesizing in my lab are cationic coordination complexes that have an anion as the counter ion. I've done quite a bit of investigation in terms of, is this going to have a huge problem? And I think that we're going to be okay. The big things we need to know from this point forward is we actually need to extend this into some in vivo systems. I'd really like to get some 3D tumor models, because one of the big sort of hurdles within chemotherapeutics is the degree to which the medicinal compound can get into the tumor cell. And so one of the reasons that NAMI-A is only removing metastases is that they find it accumulates more on the outside of the cell, and there's not a lot of penetration into cells. KP1019 reduces primary tumors, and they find that it actually penetrates further into cells. And so these two compounds work by drastically different mechanisms, it seems. And so we really need to learn more about these cobalt complexes and to see if they might provide some useful medicinal properties in different cancer cell lines. So because we weren't able to grow single crystals due to the high degree of solubility within polar solvents, one of the things we switched gears on in my lab was to change out the ligand ever so slightly. I hope you're laughing at this picture. We all need to laugh right now. But these two students worked primarily on this part of the project. So we took 1-methyl-imidazole. By adding that electron donating group, we were hoping to increase the stability of the cobalt complex while also changing slightly the organic solvents it might be soluble in. And we were hoping that this would be close enough to the imidazole compound that we would learn something about the structure in terms of single crystal X-ray diffraction. So this was sort of the goal in this particular study. And the two students that worked on this, so Delaney Winder is now a first-year grad student at Portland State, studying bioinorganic chemistry, and Robert Herman he's studying inorganic chemistry as a first-year graduate student at LSU this fall. And so both of these students helped me find the conditions, which we just had to tweak ever so slightly to set up a reflux, right, with our, again, beautiful cobalt-3 pyridine complex from the 1906 literature to provide our cobalt-3 source. And again, we used methyl isobutyl ketone. It turned out that worked really well in terms of reflux conditions. I should have mentioned that the previous cobalt-3 imidazole complex that we published on, we were actually able to get 80% yield, both in micro and macro scale in that compound. So that was a really high yielding, successful reaction. One of the red flags that should have come up on this particular project was the low yield we were getting. So we were getting a really low yield on this reaction. We thought this would be a relatively simple replacement with the methyl group added onto the imidazole. And it turns out, of course, the best laid plans don't turn out to be the easy answers. So one of the things we found is that when we first complexed this ligand onto the cobalt metal center, we again took some proton NMR, and we found that we were getting primarily a high symmetry product that was in fact attached to cobalt. Again, we did those doping experiments to show it wasn't free ligand, but you'll also notice that there's some impurity peaks. There's some shouldering like on that D methyl group that's assigned there. There's a shoulder on that. So we knew that we were getting more than one species. And again, using the tools that we had available to us, the first thing I did is said, let's look at these crystals under the microscope. This was a fairly crystalline product after the 2-hour reflux. And I don't know how well you can see, but we were seeing some co-crystallization. So we had a green product, which we consistently see for cobalt-3, but you'll also see some flecks of blue in there. And we were able to see a lot more of this blue. Usually blue to us indicates that we have some cobalt-2 contaminant within our system. And so this is a beautiful reaction, by the way, and students love to run reactions in my lab because they're highly colored. And so the very first round bottom you're seeing, the cobalt pyridine complex that we start with is a very glittery green product. We dissolve that with a little bit of heat and methyl isobutyl ketone. During the course of the reflux, we see a color change and we see bluish color, which always makes me nervous because that usually implies reduction might be happening. And at the end of the reflux, it goes back to colorless and we get a new formation of a green product. But I just showed you that formation of the green product, which isn't completely pure by NMR. And we also see some different coloration within the crystals. And so we've also tried recrystallizing this. We've tried different purification methods, and we've sent it off for elemental analysis. And this is another one that's kind of going back to look like indazole. The elemental analysis isn't matching the predicted structure with the high degree of symmetry with 4 1-methylimidazole ligands attached to the cobalt center and the trans-chloro groups. Our elemental analysis is actually matching much more closely that we have 3 methylimidazoles attached to the cobalt metal center. And so we're still investigating and trying to find the right conditions to have very pure forms of this product to figure out exactly what's going on. We have been able to solubilize the crystallized form of this after the reflux and methylene chloride. So we have been able to open up our repertoire of organic solvents to try to grow single crystals. We just haven't been successful enough in maintaining the original structure after recrystallization and getting a highly pure form. So that's what we're working on in my lab right now. The last batch of crystals that we grew in methylene chloride took about a month, which is really hard with undergrads to wait that long. And so we're trying to find some better conditions to get some single crystals of this. I did want to show you that this one also looks really similar in terms of the UV vis. So the 1-methylimidazole has these beautiful isosbestos points. We see a similar shifting like we saw in the imidazole complex. And so I'm confident that we have a really cool, consistent new product. We just need to be able to purify it. So the last thing I was going to tell you about is, I've told you about pyridine. We've substituted that for imidazole, 1-methylimidazole. We're still working on indazole. And I have some other ideas for some other ligands that bring about some other possibilities, like some of these can create bridging cobalt complexes, and they have different pKa's and different Lewis basicities. And so these are some of the things we're thinking about and trying in my lab. I just recently received some funding. Fort Lewis College is one of the partner institutions with University of Alaska Fairbanks on this NIH BLAST grant. And so BLAST is biomedical learning and student training. And so I just recently received a grant from this BLAST program to be able to pay myself and students over the summer to continue work on this project. So I'm super excited to continue working on this and hopefully figuring out some of the mysteries that we haven't yet discovered. So all of the work I showed today has been funded by several different sources. So the NIH Maximizing Access to Research Careers Award, the Fort Lewis College Foundation, Fort Lewis College Faculty Development, and then a couple of collaborators within my department and in the biology department. Those are all the students I mentioned today and all the amazing things they're doing. So thank you so much for the opportunity to share some of my research with you, and I would be happy to take any questions.
Awesome. Thank you so much, Amy. Fantastic seminar. It was really cool to see the variety of techniques as well as the variety of undergraduates you have enabled, especially when a lot of them are my colleagues as well. So we can go ahead and use the rest of the time for any questions from the audience, and feel free to just speak out.
Hi, Amy. This is Tom Richmond. I'm a fellow inorganic chemist, and one of my very first graduate students was a graduate from Fort Lewis before you were born, probably. I'm curious about cobalt starting materials, and I would have guessed pyridine, is a pretty good base and a pretty good ligand, and it wouldn't have been my first choice for a cobalt-3 starting material. I know it can survive chlorination, so maybe that's why you did it. But are there other weaker ligands like nitriles or, and really your imidazole is less basic, isn't it, than pyridine? So I don't understand this, and we'd love to have more great cobalt-3 starting materials.
Yeah, I would love to have more great cobalt-3 starting materials as well. It's probably not the perfect starting material, but it has been really useful for us. It sounds like you're pretty aware of the lack of cobalt-3 starting materials, and especially the lack of those with only monodentate ligands attached. So we did try some other cobalt-3 sources. I dug into the literature quite a bit, and we tried synthesizing some other cobalt-3 things, and they just weren't consistent and pure. And so even though pyridine's a pretty darn good Lewis base, as long as the ligands we're trying to attach have a higher boiling point, we've been able to displace those. And one of the things I worried about early on was, were we going to get a mix of ligands? So were some of those pyridines going to hang on? We actually haven't seen any evidence of that so far. So I'm totally open to other cobalt-3 sources that you might have in mind, but I haven't been able to find one that works quite as well as that one yet.
Interesting. Yeah, no, it'd be interesting to look just at the fundamental, since inert versus labile seems to be a really broad range, and they're all cobalt-3. It might be interesting, even in your pyridine starting material, whether you could do good kinetics by washing in deuteropyridine. That might be a nice NMR kinetic experiment. That's probably slow enough that you could do it in an easy way. With your imidazole, it looks like when you put it in water, it comes off pretty fast.
It's really fast. Yeah, and in fact, I've been collaborating with one of my colleagues who's a physical chemist, and he loves to write lab view programs. And so he's super interested in my cobalt-3 compounds because you can measure the kinetics on a time scale, right, that's in hours. And so he's been writing programs to actually try to fit some of our kinetics of ligand substitution reactions. And so we have been investigating some of these things, but you're right, I haven't really gone back to the pyridine compound and really investigated the kinetics of that one so much. It's a fairly highly studied complex, but I haven't gone back to look more thoroughly. We could definitely do some more investigation on that starting material. Yeah.
Oh, very nice work.
Thank you very much.
Hi, it's Matt Sigmund. I have a similar question, I guess, is the question is, can you use substituted pyridines just to also look at the kinetics? What one I would use is maybe the CF3 or the fluorinated one, so you can do fluorine NMR, which would be super easy as well. And then also you can get a sense of this, of the stabilities, perhaps that could allow you to look at other heterocycles with the same basicity range.
Yeah, it's definitely an idea I've had, especially because I'm teaching Inorganic 1 right now, and we've actually been they're practicing for their last take home exam, which is sitting piling up on my desk right now. But we've been talking about the how the basicity is impacted by electron donating versus electron withdrawing groups, and so that's definitely something that I have thought about. We actually have a brand new 400 megahertz NMR sitting in crates in the hallway at the very moment. And so our NMR is kind of slowly dying. I'm not sure if we have the capability to run fluorine 19 NMR or not, but it's definitely something I have thought about in terms of just going back to the basics of the inorganic chemistry and looking at changing the electronics, right? And changing out the Lewis basicity of the incoming ligands. So it's definitely something I've thought about, just not something I've found time to do yet, but I definitely appreciate the suggestion.
Yeah, I mean, the fluorine NMR, if your NMR doesn't do it, it's unfortunate, but that's really nice because it just gives you such a clean readout. We use it all the time we actually look at cobalt complexes with bidentate ligands and palladium and other metals, and we use fluorine NMR all the time to take all the gibberish out, and for undergraduates especially, it's nice.
Yeah, thanks for the idea. I'm going to go check out the probe on the new NMR. We're excited to have that installed over winter break. So.
Yeah, most modern NMRs have four-channel probes, carbon, fluorine, phosphorus, and proton. So hopefully,
right,
what you guys got.
Yeah. Okay. Fingers crossed. But that would be something fairly exciting to do. We did at one point. Getting into the fluorinated things, we thought about using fluorinated benzene as solvent for recrystallization to try to increase polarity of things. We tried all kinds of random solvents I would have never tried and trying to crystallize out some of these complexes. But the fluorine NMR is definitely a great idea and a nice probe that hopefully we have access to be able to analyze these compounds. Yeah.
Hi, Dr. Morris. Thank you so much for your talk. I have a more biological leaning question. You mentioned the poor solubility with some of the cobalt complexes, and I was wondering if the ruthenium drug itself has poor solubility and how they dose that.
So that's a fantastic question. So it turns out KP1019, let me see if I can go way back here for a second, just to the structure of those. So it turns out that KP1019 actually has very low solubility. And they did most of the clinical trial work on KP, I think it's 1339, which is the sodium salt instead, which greatly increased solubility. But if I'm not mistaken, both of these are intravenous injection. And I know there were a lot of side effects that developed at the injection site. So that's kind of where these are currently. NAMI-A is very soluble in water, but so soluble that they sort of call it a ruthenium rocket, and that all the ligands just seem to come off really quickly in aqueous systems. So yeah, it's a great question. Did I answer all of that question?
Yeah, thank you so much. I had maybe a follow-up question in that area. You also mentioned that they see a buildup of, I don't remember if you said NAMI-A or KP119, around the outside of the cell versus having good permeability, which makes sense if it has poor solubility. But do you know what the transport mechanism is for these? Ruthenium and cobalt are not natural metals, so I would imagine there's not much.
So one of the reasons ruthenium had so much focus early on in terms of bioinorganic medicinal compounds is because it's right below iron on the periodic table. But it's still really hotly debated if ruthenium can be transported within the body by similar mechanisms of iron. And so one of the things we do know is that these ruthenium compounds get distributed all over the body. So there is a high biodistribution of them, but the transport mechanism is another topic of high debate. There was quite a few papers claiming that you could transport these by the same mechanism that transferrin works by, but you'll find an equal number of papers that counteract that statement. And so it's a great question. And again, it becomes a complicated one just because of, these are also octahedral D5 low spin complexes. They're supposed to be kinetically inert. And what that means in terms of the d orbital splitting pattern is that you have all 5 electrons occupying stabilized orbitals. And so what you predict is that they won't undergo substitution very readily based on the stability and where the electrons are occupying. However, we see this high degree of ligand lability. And then the other thing that happens within inorganic complexes, so I'm looking at cobalt, which is first row, and so the D to D splitting or the stabilization is less, and then ruthenium in second row, that actually gets higher. So there's this really interesting sort of thing going on where we define these as kinetically inert. But I even teach this in my class. What does kinetically inert mean? Well, it's a definition, right? So it means it has a T1/2 of greater than 1 minute. Well, that could mean a lot of things. And so, there's a high degree of potential in terms of swapping out ligands and different things happening. And then when you think about concentration issues, like you're putting these in a biological environment where you have a very high concentration of water, and we know that these undergo equation reactions. And so yeah, things get complicated in a hurry.
Thank you so much.
Yeah.
Hi, Dr. Morris. Thanks again for joining us for our Curie Club colloquium. We really appreciate it. I had a question similar to Natalie, actually. You were using a cell line with a collaborator at the college, and I was wondering what cell line were you using? Were they human cells, or were they a different type of cell line?
Yeah, it's a good question. This is something I've learned over time too. It was a human lung cell line, actually. Maybe not our best cell line for learning about, but one of the things I have learned throughout my time and looking into the literature is a lot of people use cell lines that they have readily available to them. So our initial study was really just about what can we initially learn about these? Since then, I've talked a lot with my collaborator. We'd love to use some 3D spherical tumor models, right? That would be ideal. That's kind of where my thinking is headed. But there's no one at Fort Lewis that directly does that research. And so a lot of this too is finding what are we capable of doing with undergrads, where is the expertise, and what can we gain the most info out of. So I would be very curious to look at these in other cell lines. I'd probably start with the most popular cell lines that Namier and KP1019 have been most successful with. That would be sort of ideal from this point forward. This was a very initial study just to gain a little bit of information about these. Yeah.
Oh, yeah, definitely agree. I was just curious.
Yeah, no, thanks for the question.
Yeah, of course.
All right. Any other questions from the audience? I actually had one small one. Is just, so you said that that's kind of the direction you all are heading, is kind of replacing the ligands, figuring out the electrochemical properties, figuring out cytotoxicity properties. And the ligands you chose are more focused on the kind of electronics of the cobalt. Have you looked into any ligands that could help cell permeability or kind of help the biological side?
So I didn't mention this, but one of the reasons we were really interested in imidazole is that there's a lot of evidence that things like ruthenium and cobalt work really well with histidine side chains on protein structures. And so imidazole is the side chain for histidine, right? And so we have definitely been thinking along those lines the whole time, and looking at what the most common things in biological systems would be. So that's definitely, while we got inspiration from NAMI-A, it definitely went beyond that in terms of the choice of that particular ligand. Yeah.
Awesome. Thank you so much.
Yeah.
And if that's all the questions we have, I do have one announcement is that our other two Curie Club colloquium events today are two Curie Club coffee talks where we have our guests and just talk casually about their career in STEM and bring any questions to the table, you feel free. So those are today with Professor Amy Morris from 2:30 to 3:30. And then our Tuesday seminar guest, Professor Renee Robinson from 4:30 to 5:30. So please just reach out if you need that information again. And Amy, thank you so much for your talk. That was just fantastic research and a great story along the way. And we look forward to meeting with you more today.
Thank you so much for the invitation. I look forward to chatting with you all later.
See ya. Bye.